Okay, it's a little bit all over the place, but it's okay. We'll make it work. Okay, I'll just have to. I have a way. I know how to make that a little bit more presentable, but I'm not really trying to do that right now. 225. I think we go until what? Somebody in the chat for me. Type, what time do we get out of here? It's like, is it 3:05? I hope it's not 3:05. Maybe it's 3:15, right? I think we go until 3:15. I'm gonna go until 3:15 unless you correct me. Okay, cool beans. All right. All right. So a little over 30 minutes. That's fine. We'll do the best that we can. Are you active? Come on. Okay, let's close you out because I know how you like to do. This one, right? Okay, let's try this again. There we go. Oh, you can't see that. Let's go here. Can we move you down? That looks a little bit better. It's still kind of weird, but it'll do for now. I can't get that to go away right now. Hide video panel, loading media controls. That's okay. Okay. It looks a little weird, but it's okay. Okay, so we're going to continue chapter 1 with section 1.4, a library of functions. We'll do the best we can to just, we want to focus on this section for this week. Okay. Let me see. So if we can get through 30 slides today, that'll be a pretty good rhythm. So we have let m and b be real numbers. Then this function f of x equals mx plus b is called a linear function. This is similar to like y equals mx plus b, right? If m equals 0, if our slope is 0, then we're going to have f of x equals b. This is going to be a constant function. Oh, we got a minute and a half. If the slope is 1 and the y-intercept is 0, then we get what's called the identity function. It's like y equals x, all right? So let's do this color pops a little more. So on the left, we have a graph that has a positive slope. Notice that as we trace it left to right, it goes up. The one on the right with a negative slope, as we trace it left to right, it goes down, all right? Okay. So where we have f of x equals b, again, let me see. I'll let them in. I have to update the tennis a little bit later. That's correct. Let me see. Can I just hide this? That might work if I can hide. Give me just a moment. I'm going to just try to update my attendance. Oh, that's not what I wanted. You're not behaving the way I wanted. All right, that's fine. I'm going to go here, and we should be good to go. All right, that'll work. And put you back. I'll make it like that. Okay, that'll work. Oh. Okay. It's okay. Yeah, no, I sent a different link. I'm doing a different link every time we meet, so it's okay. You got full credit, so you're here. And actually, I'm just about to lock it out, so hopefully you got in just in the nick of time. Someone said check, so you did the right thing. I'm gonna go ahead and lock up the meeting, though. Okay. All right. So let's keep it moving. So again, if we have y equals b, that's going to be a horizontal line, right? The slope is 0. So that's going to be a flat horizontal line through y equals whatever that number is. If the slope is 1, this is called the identity function. So the one on the left, this is called the constant function. Are you slowing down? You are kind of slowing down. Hang on. I can close that. And let's go back here. I think it was this one. Maybe I can shrink this down. I can make that a little bit smaller. It actually helps out a lot. Okay. So again, y equals to a number. That's going to be a constant function. That's going to be a flat horizontal line through y equals whatever that number is, right? And then f of x equals x. That's called the identity function, and it's going to be a diagonal line like this. So what we're doing is we're building a collection of basic functions, and that we're going to use to kind of start graphing some of these notions. So here we're asked to write a linear function g for where g of 1 equals 4 and g of -3 equals -2. Okay, so whenever I work lines, I usually like to have 3 equations ready to go. The first is what? The slope formula, slope between 2 points. That's going to be y2 minus y1 over x2 minus x1, right? It's a slope formula. Then we have the point slope formula. We use that whenever we're given a point and a slope, and that's going to be y minus y1 equals m times x minus x1, all right? So if you have a formula sheet, these are good formulas to add to that sheet and just have it ready to go whenever you need it. And then we have the slope-intercept formula, slope-intercept formula. And that's the y equals mx plus b. Okay. So here we have an ordered pair. So when x is 1, y is 4. When x is -3, y is -2, right? So we want to find a line, the equation of a line that goes through those 2 points. So whenever I have an ordered pair, I like to automatically go x1, y1, x2, y2, right? Just like that. Okay. So then I usually like to do the slope-intercept formula, but to do that one, we need the slope, right, and the point. So I'm going to use my slope formula. Again, the slope formula, one of my mentors would say, every time you use a formula, write it down, right? That constant repetition helps to ingrain it into our memory, okay? So again, the slope formula is y2 minus y1 over x2 minus x1, okay? So then y2 is -2, y1 is 1, x2 is -3, and x1 is, sorry, I did something wrong. Let's back up. Y1 is 4, and x1 is 1. There we go. So then if we crunch these numbers on top, we get -6 divided by -4, which becomes a +3 by 2. So we have our slope. Now we could use the point slope, and that's how I used to always do it, but then my students used to do slope-intercept, and so I checked it. It actually worked, and it's actually legit the way they were doing it, so I borrowed that technique from them, as just starting there. So then if we're going to do y equals mx plus b, let's plug in what we have. I'm going to choose the first point, because those numbers seem easier. They don't have negatives, so I'm just going to choose them. We could choose either point. So if my y is 4, my slope is 3/2, my x value is 1, the only thing we don't know is b. So then if we solve, b is going to be equal to 4 minus 3/2. So that's going to be what? 8/2 minus 3/2 to give us 5/2, right? So then our equation is going to be y equals 3/2x plus 5/2. Okay. If you have questions, you're going to have to use the chat. And I want to shrink this down just to make it look a little bit more presentable. Just to kind of trying to squeeze it in there. Okay. And keep in mind that everything that you see me writing, I'm going to load a copy into our box folder. So if you go to our Blackboard page, the last folder, the item number 7 should be a box link. You can click on that, and you should be able to access any of the notes that we had on any given day. And also, I'm streaming this directly to YouTube, so if you needed to go back and watch any of our sessions, those should be on YouTube as well. Okay. So they're kind of doing the same thing we did. They have the slope, okay, 3/2, and then you see the formula there. So let f be a function and let x1 and x2 be any two numbers on an open interval. Then the symbols a and b may be represented by real numbers, negative infinity or positive infinity. Then we have the following. This is the notion of what we mean by an increasing function. So we say f is an increasing function on an open interval ab if x1, whenever x1 is less than x2, this implies that the corresponding y values, f of x1 is less than f of x2. So the simple explanation is increasing means as we trace the graph left to right, it goes up. It goes up, right? So increasing means whenever, in a graphical sense, or a simple explanation is as we trace the graph left to right, it goes up over some part of the domain. Okay. Decreasing is similar. As we trace the graph left to right, it goes down. We say a function is decreasing on an open interval if whenever x1 is less than x2, that implies f of x1 is greater than f of x2, right? The simple explanation again, as we trace it left to right, is going down. Right, it goes down. And then we say a function is constant whenever x1 is less than x2 on an open interval AB. This implies that f of x1 equals f of x2. The simple explanation, as we trace the graph left to right, it stays constant or flat. Right? It has a slope of 0. Right? So we call that a constant function. So here on this graph, we're asked to find the intervals over which this function g is increasing, decreasing, or constant. All right. So notice as we trace this left to right, let's do it like, let's do this one like this, like this. As we trace it left to right, what is it doing initially? Is it going up? Is it going down? Or is it staying flat, right? As we trace it left to right, notice initially it's going up. Right? Up until this x value. What's this x value? Here. So the x value there is going up. What's the x value there? So the x value there is -2, right? So we say that the function is this one, right? We say it's increasing. That's too thick. Undo like this. I think this is the right one. Is it this one? We said the function is increasing from the far left is -infinity up until x equals -2. We say it's increasing from -infinity to -2. Okay. Then the next part, man, I like these updates. I'm sorry, I'm kind of geeking right now in my mind. Like, so I'm using this app called Notability, and they've recently done like several updates. For instance, being able to do dash lines. They've actually done a lot of updates that I think are fantastic. There's one that they really need to do, but you have to use the app to know what I'm talking about. But I'm just geeking about this. Like, I can do a lot of different figures, like transform them to like straight edges. It's kind of nice. I like it. Anyway, don't mind me. So then from -2 up until 3, we see that the function is staying constant or flat, right? So it's staying constant from the x value of -2 up until 3. And so for this discussion, I like the way that this text describes it. We always use open intervals for this discussion. Then we say it's decreasing. It's going down. I'm going to match it up with this guy. Okay, here, let's do this. Let's move u. Nope, undo. Move u out of the way so that these can match up. It's fine. And then I'm going to put you back. Okay. And we said that it's decreasing. What's the x value from 3 to infinity? Okay. All right. So again, I'm monitoring the chat if you have questions. Okay. So we said it's increasing from -infinity to -2. It's constant from -2 to 3, and it's decreasing from 3 to infinity. Okay. So we say if a is in the domain of a function, we say that the value f of a is a relative minimum of f. If there's an interval x1 to x2 containing a such that f of a is less than every y for every x in the interval, right? We say that this value is a relative max. So the simple thing is like, okay, if a is in the domain of the function, we said that the value f of a is a relative minimum if it's basically less than all the other nearby y's, right? It's like the bottom of a valley. So in a graphical sense, the local minimum or relative minimum is going to be less than all of the nearby y values, right? And then a relative maximum is going to be greater than all the nearby y values. It's going to appear like the peak of a mountain. How is the infinite number not negative if it's going down? So the infinity is not talking about up or down. This is these intervals are talking about based on the x-axis, based on the domain. So this is talking about from the left to the right. So as we move towards negative infinity along the x-axis, the y value is going down. As we move from -2 to 3 on the x-axis, the y value stays constant. As we move from 3 to positive infinity, the y value, sorry, I said that totally wrong. As we move from negative infinity to 2, the y value is going up. As we move from -2 to 3, the y value stays constant. And then as we move from 3 to infinity, the y value is going down. That's what these concepts mean, right? So this positive infinity is talking about is based on the x-axis. It's going off to positive infinity off to the right. So the further and further we go to the right, the y value goes further and further down. Right? So these are talking about the x-axis. Increasing is talking about the y value, y value, y value. Hopefully that makes sense. Okay. So again, relative min is going to be like the smallest value of all values of the nearby y values, and the relative max is going to be the largest y value of all the nearby y values, right? So for instance, on its we see two examples of the relative max, right? The nearby y values, that's going to be one of the peaks. This is also a relative max. This is a relative min. It's the bottom of a valley, right? So in a graphical sense, it's fairly simple for these examples. So then another notion that we have is what we mean by a function being an even function. We say a function is even. So the definition of even for this context means when we do f of negative x, it gives us f of x. All right. So if we replace all the x's with negative x, we get back f of x. The graph of an even function is symmetric with respect to the y-axis. All right. So that means we can actually fold it on the y-axis, and the two halves are going to be mirror images of each other. They're going to match up. So then the definition of a function being odd means if we replace all the x's with negative x, then we get negative of the original. All right. In the previous, if we replace the x with negative x, we get back the original. But in this one, if we replace x with negative x, we get negative of the original. A function being odd is the same as origin symmetry. It's symmetric with respect to the origin. So origin symmetry is like where if you have a graph, it's going to pass through the origin. And whenever you have x comma y, we also have negative x comma negative y. It's as if we put our thumb on the origin and we cut it across like the x-axis. And if we rotate it 180 degrees, the top half is going to match the bottom half. To me, in a visual sense, that's the simplest way to visualize origin symmetry. But basically, whenever every point that we have on one part of the graph, like every time we have x comma y, we also have negative x comma negative y. So it's going to be points that are equidistant and symmetric about the origin, right? They're going to be like if the origin is my nose, right? We're always going to have points that are equidistant from the origin. It's going to kind of behave like that or whatever. That's the notion there. But to me, the simplest way to explain it, if we put our thumb on the origin and rotate the top half 180 degrees, is going to match the bottom half. I consider origin symmetry like rotational symmetry, but it's all in how you like to articulate it. So y-axis symmetry means that it's something like a parabola, right? You can fold it on the y-axis. The y values are going to stay the same, but the x values are going to be opposite in sign. One's going to be positive, one's going to be negative, but the y values stay the same, right? So y-axis symmetry, we can fold it on the y-axis, and they're going to match up. Determine whether the functions are even, odd, or neither. So let's do a quick test. All right. So we're going to start with, first we're going to do g of negative x. Well, first I'm going to replace each x with a blank set of parentheses. This is part A. I'm going to replace each x with a blank set of parentheses. Then, actually I'm going to need more space than this. Let me just clear this out. me add a page, and let me get a copy of this. I don't need that one. And I'm going to take this. Let's copy. Awesome. And we want to paste that right here. Boom, just like that. This brings you out. Looking good. Then we're going to go to view. Like this. And I think we're ready to rock and roll with this example. Paper. Alright. My man, my man. Okay. I'm totally like just trying to keep myself awake. We only got 15 minutes? No! The time goes so fast. It's so sad. But actually, as long as we make it this, like 10 more slides, we'll be right on track with the rhythm that we need to be doing. Okay, so let's test for even, odd, or neither. I'm laughing because like I feel like I should. I want to test my my Denzel Washington impersonation, but I know I can't do it, so I'm not even gonna try. But check out this movie again. Shameless advertising for other people. Again, I get tired of doing that, but one of my favorite. I had this movie in mind. It's called Game Night. It's hilarious. Check it out. The guy, he does a fantastic Denzel Washington impersonation in that movie, and that's what I had in mind when just a second ago. So let's do a test for even, odd, or neither. Right. So if we're doing part A, we're going to do g of negative x. Right. Let's do our blank parentheses first. Right. So we're going to replace each x with a blank set of parentheses. Cubed minus 4x. Right. And then what we're going to do, we're going to test, we're going to replace each x with the blue thing, negative x. Right. So now let's simplify. All right. Let me, I like to kind of do the following. I like to have my vertical line and just line up my equal signs, right? It just makes it, I don't know, much more neat and presentable. So if we have an odd number of negatives, if we have 3 negatives, is the final result going to be positive or negative? If we have an odd number of negatives, is the final result going to be positive or negative? It's actually going to be negative, right? That's going to be negative x cubed. Double negative there is positive, right? Notice here we can factor out. Let's factor out a negative and see what happens. So this is the same as negative of x cubed minus x. Is that x cubed? Oh, I forgot about the 4, right? There needs to be a 4 there, and there needs to be a 4 there. So a 4 here, and a 4 there, right? Okay. So notice that we have negative of the original. So this is equal to negative of f of x, which is the original. So then, whenever, oh, not f, sorry, that needs to be g, just be consistent. So if we have g of negative x equals negative g of x, that's the definition of a function being odd. That means this function is odd. That's the definition of a function being odd. Okay. We got 15 minutes. We're gonna take advantage of this 15 minutes. Yeah, let's keep going. Let's do part B. Again, we need to make it to slide 30 if we can. Part B, the original is, let's write the original. F of x equals x squared plus 5, right? Let's add some more paper. I don't know about you guys, but I'm loving like writing on this device. It's so much fun. Because then I have endless paper. I could just keep going. I don't have to like be messy, deal with walking around. Anyway, okay, so let's do the same thing, right? We're going to replace each x with a blank set of parentheses. X squared plus 5. And then we're going to replace each x with negative x and see what happens, right? Then I'm going to go like this. This is fine. I'll get rid of it later. Bring down our equal sign. So negative x times negative x is a positive x squared plus 5. Is this the original? This is indeed the original. So notice that f of negative x equals f of x. So then that's the definition of a function being even. Okay. Style like I like how bold that is. Okay. Okay. And let's do part C. Yeah, I can't worry about that. So then part C, we have h of x. We got this 2x cubed plus x squared. Okay. And let's do the same thing. So we're going to replace each x with a blank set of parentheses, 2 times x cubed plus x squared. We're going to replace each x with negative x. Yeah, even is the same as y-axis symmetry. Odd is the same as origin symmetry. There's nothing for x-axis symmetry. Okay, if we keep going, that's going to be a negative 2x cubed plus x squared. I think even if we factor out a negative, we don't get back to the original. So this one is going to be neither. Okay, that one's going to be neither. Okay, let's see how do we do. I think I will like to condense this down to one page. Oop, that's not the right tool. Okay. Let me get rid of this. Delete. Let me do a paper. Take that back. And then let's go to the view. Single page. Okay, that's what we got there. Odd, even, and then neither. All right, odd, even, and then neither. Okay. So evaluating, let me see. I want to keep going. Once I hit 30, right at about 30, I'll stop. To evaluate f of a for a piecewise function, determine which line of the function applies to a number a, and then evaluate f of a using the line chosen in step 1, right? So we have let f of x be this, find f of 0 and f of 2, right? So for instance, if we're going to do f of 0, if x is equal to 0, do we use the first line or do we use the second line if x equals 0? If x equals 0, do we use the first line or do we use the second line? Right? So if x is 0, notice that 0 is less than 1, so we're going to use this line. Right? So let's actually go a little bit darker. So then f of 0 is going to be, in this case, it's going to be 0 squared, which is just 0. Now if we do f of 2, if x is 2, notice that 2 is not less than 1, but 2 is bigger than 1, greater than or equal to 1. So that means we're going to use the second line. So that means we're going to do 2 times 2 plus 1. What is that? 5. Right? Okay. So we got 0 and 5. We got both of those results. So let f of x be this. Sketch the graph, right? So to sketch the graph of a piecewise function, you just graph it like normal, but then the first line only, like in this case, the first line only applies when x is strictly less than 1. The second line applies when x is greater than or equal to 1. Let's see this in action. Let me start by getting a copy of this original. I don't need this. I just want this guy here. I think this will be the last one for the day. I should have just got there instead of saying that, but that's okay. Let's copy. I'm going to add a page right there. Come on. And I'm going to drop you right here. Boom, you're looking good. Just like that. Let's do the view as the seamless. And let's get some graphic going. Sexy. Okay. All right. So let's graph these like normal, right? Normal. These are both just lines, right? So I'm just going to graph a line. It's all kind of centered around 1. So I'm just going to do a regular XY plane. Just a few points, right? I don't need too many. All right, so the positive X, actually, let me try this to get all that. I got to get used to that. All right, so we got this. So this will be the positive Y in this direction. This will be the positive X in this direction. Let's go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's enough, right? This is going to be the origin. 1, 2, 3, 4, 5, 6, 5. -5. Okay. I'm watching the clock. So now let's just graph the first line like normal. Anybody got a favorite color? Anybody feeling any kind of color? Anybody got a favorite color? First one I see. Nobody? Red. Guys, we always choose red. It's so interesting to me. All right, we'll do this first line in red. Just want to fill with red. Okay. And we'll graph F in red. So to graph a line, this is already in the form y equals mx plus b. So our y-intercept is 1. Our slope is -2, right? So if we go down 2 and right 1, we can put a point. Let me keep going. Down 2 and right 1. Down 2 and right 1. Here. Okay, so from about there. And then this way, let me see. If we go up 2 and back 1, we're here. Up 2, 1, 2, 3, 4, and back 1 is here. Not there, right? So basically what I'm doing is, can we do a double line? How do I do that? I guess that'll work. Okay. So we didn't do that right. That'll work. Okay. I'm coming, guys. Okay, that's it. Let me undo. Redo. Okay, I'll go with that. Okay. So that's the graph of the red, and we're going to come back and make a change to that. And then anybody else? We're not done yet. So anybody else have another favorite color? Another favorite color from anybody? Nobody? Yellow. So usually when students request yellow, because I can't see it, I'm going to do orange because it just doesn't show up that well. So we're going to do this one in orange. Okay, let's go style. We want to fill it with orange. Okay. Okay, we're almost there. Okay. So the second one we'll do in orange. Okay. So the y-intercept is 1, so it crosses the x-axis at 1, and the slope is 3. So this one we go up 3 and right 1. up 1, 2, let me see, 1, 2, so 3 would be there, and right 1 would be about there. We can go 1, 2, 3 in this way. 1, 1, 2, 3 in this way. And then we can do one about here, right? So we're connecting from here to here, right? So again, to do the piecewise, you just graph it like normal. There is a caveat though. And I know that at least one person notices it. Let me get rid of, did I miss my point? Wait a minute, I didn't do something right. Somehow I got off. 1, 2, yeah, I see it now. Let me just back up. Okay, let's try that again. 1, 2, 3, and 1 is here. 1, 2, 3, 1 should be about there. 1, 2, 3, and 1 is here. 1, 2, 3, and 1 is here. And let me take it a little bit further, right? So we're going to go from here to here. That looks good. Okay, that looks better. And let's just be consistent. I see the time we're about to wrap up. Okay. And one other thing I want to do. Let's do the whole thing. Get rid of this guy, and then yeah. Okay, I think I got it. Okay. So now, to do a piecewise, notice all the piecewise is several graphs on one plane. I just graphed both of them like normal, right? But now, just like Mr. Charles suggested, not Mr. Charles, Mr. Alexander, he noticed like, well, I know there's more to the story, right? So yeah, there is, right? So right here, if x is less than 1, so the red only applies if x is less than 1. So if we focus on this 1 here, do we keep the left part? If x is less than 1, do we keep the left part or the right part? Right? If x is less than 1, we're going to keep the left part. So we're going to get rid of everything on the right. All right, all of that's gone. So we're just keeping the left. Also, because there's no bar, this is going to get an open circle. Let me shrink that down. Hang on. That's fine. And then what I want to do, I want to move this to about there is good. And then fill, I want it no fill. Oh, actually, it's just a little white. Okay. Right? So again, the red only applies when x is strictly less than 1, so we did an open circle. So we only kept the left part, the part that was left of x equals 1, and we used an open circle. Make it a little bit bigger. I see the time, that's too big for me. That's better. Okay. Let me wrap up. And then for the orange, it says x is greater than or equal to 1. So we're going to keep everything to the right of 1. So let me get rid of the stuff we don't need. We don't need this guy or that or that. If I can get to that orange, let me. I'm about to let you guys go. Okay, and then let me copy this, and I'm gonna paste it, and I'm gonna put you about here. And my style, the stroke needs to be orange, and it needs to be filled in, right? Because x can be greater than or equal 1, that's gonna get a solid circle. I see the time I'm about to let everybody go, right? So that's gonna be the graph of this one, right? So hopefully that addressed that request. Let's kind of look at this paper like this. Let's go view, single, right? And then we're going to see a computer generated one. So they did that, and then you see the final right there to the right, okay? Let me make a note. We actually hit our mark. Let's use this color. Let me make a note. So I'm going to say stopped. stopped here. What's today's date? On Tuesday the 15th. On Tuesday, September 15th, 2020, at 2:25 at the 2:25 p.m. I'm gonna say, all right, whatever. It doesn't matter. I'm gonna say start here. Start here. Thursday. What's today? 15th of September 17, 2020. This is for the 2:25 p.m. Okay. Okay, guys. If there aren't any burning questions, I'll see you Thursday. Okay. Take care. I'm gonna unmute you so that you can unmute yourself if you want. Unmute yourselves. Okay, guys. Take care.
Thank you very much.
My pleasure. Like this. Let's stop streaming.